Hi, I'm Yuexin Wang. Our tool named TsmartGP will be introduced in this video. The corresponding paper is entitled TsmartGP, a tool for finding memory defects with pointer analysis. Precise pointer analysis is desired since it is a core technique to find memory defects. There are several dimensions of pointer analysis precision: flow sensitivity, context sensitivity, field sensitivity, and path sensitivity. Considering all dimensions is difficult because the trade-off between precision and efficiency should be balanced. We implement a static analysis tool named TsmartGP, which can find memory defects with pointer analysis. The analysis is flow, context, field, and quasi-path sensitive. To ensure its efficiency, we propose a multi-entry mechanism. TsmartGP are used to find uninitialized pointer errors in 13 real-world applications, and the results show that it can find more errors than other tools. TsmartGP contains 3 core components: Builder, Analyzer, and Visualizer. Builder is used to pre-process the program to be analyzed. It transforms the program to control flow automaton. Analyzer calculates function summaries and finds uninitialized pointer errors with pointer analysis. Visualizer shows all the errors and their path in source code. Here is the results interface of TsmartGP. From the reports, we can know the type and confidence of the selected error. The path which leads to the error is given in the left. Click the path and its corresponding source code will also be presented. For example, there is an uninitialized pointer error in the sample program. The error occurs in line 11, and its path is given in the left. Our pointer analysis algorithm is developed based on Anderson's inclusion-based method. The formalization of our algorithm is shown in the right. For store operations, we have optimizations named strong update and weak update. Our pointer analysis is flow, context, field, and quasi-path sensitive. We compute a separate solution for each program point, which makes our analysis flow sensitive. For context sensitivity, we utilize function summaries to represent their behaviors. As to aggregate structures, we propose a model to handle their fields. During analysis process, we collect path constraints and filter unreachable ones. To balance accuracy and efficiency, we propose a multi-entry mechanism. Traditional static analysis usually treats main function as the only entry and analyze all its paths. In our algorithm, we treat all functions as entries. The analysis for each entry is independent. We should specify the max call depth before pointer analysis begins. For each entry, we should analyze its CFA edge by edge. For function calls within the specified call depth, we should enter their CFAs and analyze them. If the max call depth is reached, we should apply function summaries to represent their behaviors instead of entering them. We use TsmartGP to find uninitialized pointer errors in 13 real-world applications. CPP check and clone static analyzer are chosen for comparison. In column TsmartGP, the left shows the results of TsmartGP with path-insensitive pointer analysis, and the right shows the results of TsmartGP with path-sensitive pointer analysis. As we can see, TsmartGP finds more real errors, while its accuracy is also higher than CPP check and clone static analyzer. All the errors found by CPP check and clone static analyzer can also be reviewed by TsmartGP. If we make our algorithm path sensitive, there is no false positive. Next, I will show you how to use TsmartGP. Our tool can be started through these scripts. Before running it, you should set the root directory of TsmartGP, the analyzed program, and specify a directory to store outputs. After that, run the script and the program will be analyzed. In this program, there is an uninitialized pointer error, and the confidence is may. Click it, we can get the path which leads to it. Each line's corresponding source code is presented in this part. Errors can also be filtered by their confidence. That's all. Thank you for your watching.